So I would read the background on the experiment, and then I would start looking at the procedure. And when you look at the procedure, it's kind of long. And what happens is, if you follow the procedure for some experiments, you're not going to be fast enough. This is for experiments that they try to cram a lot of work into a small amount of time. And so what I usually do for labs that are going to be quite involved is I'll prepare the procedure in my notebook before lab. And that's probably what I would do for this one, because I don't want to be having to read, paragraphs worth of procedure here. Instead, what I do is I just, this is my personal preference, I just write this as little sketches, little drawings. Then step 1, step 2, etc. Other people will collapse this. There's probably only a couple of, like, one sentence you can make this paragraph into, and that'll speed things up. So if you're having trouble finishing the lab in time, that's what you should do before lab. And so that's the real pre-lab. The real pre-lab is you do at home and you prepare the procedure out. And this way, when you're reading the procedure and something doesn't make sense, then you could ask right at the beginning of lab, what's going on with this step or that step. All right, when we go to the pre-lab quiz, or the pre-lab, this would be kind of like a pre-lab quiz. So this didn't happen when I was taking classes at, say, Santa Barbara City College, but when I went to UCLA, we'd have a pre-lab quiz that we'd try to prepare for. They wouldn't give you the questions in advance. So you try to think of what types of questions would they ask in the pre-lab quiz. And so for this particular experiment, what we have is we have a sample. It's an unknown. Now, there's something known about this. This unknown contains sulfate, and it weighs 0.4892 grams. So we have a sample here. It's a solid, and it weighs 0.4892 grams. And this sulfate in the solid state here. So there's got to be some cations. Maybe there's other anions in there in addition to sulfate, but we know that there's going to be some sulfate in there. What we want to do is we want to figure out how much sulfate is contained in this unknown sample. And so let's take a look at the procedure as far as the not the step-by-step. The step-by-step procedure is like a cookbook. Take this many milliliters of water and this many milliliters of this and mix them together. So this is a cookbook style. But this we'll look at the procedure in the chemical sense here and see what we're going to do for analysis. This is a process called chemical analysis, and this is a field of analytical chemistry. In analytical chemistry, you analyze samples. You analyze them for all kinds of stuff. So, for example, in Chapter 3, we're going to see we analyze things for their elemental composition, to see what elements are contained in there and what percentage. But let me grab my pen. I forgot my pen in my office. So, what we want to know is how much sulfate is contained in this. And how we analyze it depends. This is a solid. But we could also have like aqueous solutions, liquids. And that's going to change things. And so one of the things we need to know is if we take this is unknown. And when we have an unknown, you're going to have to make sure you record the unknown number. If you don't record the unknown number, then you're going to lose max points for your unknown grade if I can't figure out which unknown you had. And so record number. When we analyze these things, we would like to, because it's we'd like to free up the sulfate, but the sulfate is locked in a crystal lattice. Ionic compounds form these crystal or ionic lattices, and the sulfates, when we think about it, they're stuck in some kind of arrangement with other ions. And all they could do is vibrate around. There's other types of motion. Does anybody know the other types of motion? Like vibrate? Translate. However, in solids, we have no translational motion. That's one of the restrictions for solids. Liquids and gases, we have translational motion. Translational motion is going from point x1 to point x2, just traveling in space. There's no translational motion here. And another type of motion? Rotational motion. The sulfates might rotate, but they probably aren't rotating in this. They're just probably vibrating in this lattice. But what we're going to do is we're going to free the sulfate so that they can, right now they're locked in the lattice, but we're going to free them so that we can capture them and analyze them. And so the first thing is we have to know, does it dissolve in water? And so normally the first thing we try to dissolve things in is in water. What happens if it doesn't dissolve in water? Well, the first thing we try is room temperature water. If it doesn't dissolve in room temperature water, do you know what we go to next? Yes. So first we try just room temperature. If that fails, then we try hot water. What happens if that fails?
Hotter water?
Okay, hot water means just keep increasing the temperature. If it still doesn't work, then we give up. Hot water could be all the way up to boiling, as was mentioned. Normally what we do is we'll try different things. Maybe it's not soluble in water. And so we try different things like alcohol. And so the first step is called dissolution. Dissolution is another word for what? Dissolving. If we could try alcohol. If alcohol doesn't work, do you know what we try? Acid. If acid doesn't work, we try. Oh, actually, this goes before alcohol, but in the CRC handbook, look at this. Acid, then we try base. If base doesn't work, we could try things like hexane. Hex, how many carbons is hex? 6 carbons. And so hexane looks like this. It's going to be a carbon chain. We draw them zigzag like this because they're all tetrahedral. 1, 2, 3, 4, 5, 6. Or we could draw them in a straight line, but if we draw them in a straight line, it doesn't show the structure as much. And then we put a CH3 on the end. What's a CH3 usually called? Like, CH3 is called methyl group. Good. And a CH2 is called a I only mentioned it once briefly, just seeing. Nobody got it? Ethyl's two carbons. on the end. So not that we do this, we just name the entire chain. But there are different ways of visualizing the structures. And different ways of visualizing is looking at little entities like CH3. CH2 is called methylene. So we have 1, 2, 3, 4 methylenes sandwiched between 2 methyl groups. That would be hexane. That's one way of thinking about it. Another way of thinking about it, this could be an ethyl group here, 2 carbons. So an ethyl and an ethyl and an ethylene sandwiched between 2 ethyl groups. They're different, but we wouldn't look at it that way. We'd look at the longest carbon chain, and that would be it. This one turns out to be a liquid at room temperature, so it's a hexane liquid. Excuse me. And so, let's say you're trying to dissolve a candle. Does candle dissolve in water? No. Does candle dissolve in hot water? You might melt it a little bit, but it's not going to dissolve. Does a candle dissolve in alcohol? Maybe a little bit, not much. Does a candle dissolve in acid? No, it doesn't dissolve in acid. Depends on how strong the acid is, what type of acid we use. If we use the next one is 7 here. Does a candle dissolve in base? No, but a candle should dissolve in hexane. The reason why is candles are non-polar hydrocarbons like hexane, except a candle's solid, this is liquid. So candles have much larger molecules. These much larger molecules have stronger intermolecular forces that hold the molecules together. And so we have this, do you remember the solubility rule for molecular compounds? And so unfortunately there is memorization in this class. You probably realize. And so solubility rules for molecular compounds are simple to remember. For molecular, it's like dissolves like. And so candles are what we call nonpolar. Hexane's nonpolar. Hexane's an excellent nonpolar solvent. And we could use that. There are other nonpolar solvents that we could try as well, but hexane's a common one. What if it fails? All these fail. You don't try these all at the same time. You try them one at a time, right? And then if that fails, then we try an oxidizing acid. Usually over here we try something called a mineral acid. And then we'll try an oxidizing acid. A mineral acid would be like HCl or acetic acid. The next thing we might try is something like an oxidizing acid. An oxidizing acid would be like HNO3. Both HCl and HNO3 are strong acids, but HNO3 is also what we call a strong oxidizer. Whereas HCl is a moderate oxidizer. It's not as strong as nitric, but it's still a decent oxidizer. HCl. And so we try an oxidizing acid. If that doesn't work, then what we do is we often go to hot nitric acid. And we're relying on different properties, so we have to be careful here because we have 2 types of properties, in a broad sense. What are the 2 broad categories of properties? Yeah, chemical and physical. Good. And so like 1, 2, 3, these are primarily physical dissolutions. When we get to 4 and 5, these are typically chemical. That is, if you're trying to dissolve it in acid, you might be destroying the thing you're trying to analyze for, And so you got to be careful. 6 is physical, like hexane. You can get the candle out of it. 7 and 8, these are definitely chemical, where the original sample might be destroyed in the process. But if you're trying to get a certain species in solution, then it could be worth it. So I'll tell you, your sample will dissolve in water, in room temperature water. If your sample dissolves in room temperature water, then we already have some clues of what cannot be in there. What cannot? If this sample dissolves in water, what can we eliminate as a possible cation in here? Because there's some cations in here. We don't know what the cations are. And there could be other anions. But there definitely has to be a cation, because can we have an anion without a cation in a solid? No, it's not possible. And so we can quickly eliminate certain cations out of here. And so this brings up the solubility rules for ionic compounds. And so probably, I want to try to give you as much memorization stuff early rather than later. But maybe you had this memorized from Chem 4. There are different schemes for this. Someone? Remember? I usually break it down into 7. Ashley, you remember?
This one has acetate.
Okay, actually we go back. Before we look at the anion, we look at the cation first. What cations are always soluble? Tanner, yeah. Group 1, and what's NH4 plus called? Yeah, group 1 and ammonium. And these are all soluble. Good, Tanner. Okay, now Ashley, go ahead with yours.
Acetate.
Yeah, acetates, nitrates. H3O2.
See? Chlorate.
Chlorates. Yeah. These are all soluble. Are these the solubility laws for ionic compounds or solubility rules for ionic compounds? These are rules. And so, for example, there are some insoluble nitrates, the weird, and there are some insoluble acetates. And there are some insoluble group 1. So one that you probably wouldn't have to worry about it so much, because one of the well-known insoluble sodium salts is sodium uranyl acetate, which contains uranium. And so most likely you would never be working with that. And so unlike laws, rules will have many more exceptions to that. All right, next. Chlorides. Chlorides, bromides, and iodides. Rory, you remember these? All right. Chlorides, bromides, and iodides. These are soluble, except which ones? Silver, yeah. Ag plus. Mercury 1 or mercury 2 or both? Mercury 1 actually. Mercury Hg2 2 plus. That's mercury 1. The charge on each mercury, the whole thing's 2 plus. You have 2 mercury, so each one has got to be 1 plus. but they come as a group. You know, if it's like you go to the store, you have to buy a pair. It's going to come in a pair, like if you go buy shoes. And lead 2. Yeah, good. So maybe these aren't as fuzzy. When you don't use these for a while, they're easy to forget. Most people don't use these much. Why am I not? All right, that's weird. All right, what's the next anion that we look at? Not sulfites. Or did you say sulfites or sulfides? Not sulfides, but close. Sulfates. Sulfates, these are soluble, except for which ones? Except for calcium. Well, I'd like to do it in this pattern so it's easier to remember. I'd like to go silver. Silver, I have to put an asterisk here because silver is borderline. You know, silver is what we call slightly soluble, so it might not precipitate with sulfate, or it might not stay as solid. You might be able to dissolve it. Okay, silver. I'm going to go with lead. Mercury. Okay, silver, lead, mercury. I usually do silver, lead, mercury. Sorry. So let me do lead. And I should change the one above because normally I do this. I do silver, lead, mercury. The reason I do this is because both mercury 1 and mercury 2. And so it goes silver, lead, mercury, mercury. Calcium, strontium, barium. This last column gets cut off. All right, but before I move on here, tell me why fluoride is missing. Why isn't it fluorides, chlorides, bromides, and iodides? Fluoride is a member of the family that's missing. Does somebody know why?
Does it have something to do with its electronegativity?
Well, it has to do with its small size. It's very small. Fluoride already has an electron, and so it's not very electronegative in that sense. It's more electropositive, means it wants positive charge rather than negative charge. And so something like fluoride, let me wait for this. Okay, might have run out of memory here. Let me pause the video. Save it. Okay. Does somebody have the answer? What? It has to do with the small size. I don't know if that's enough. So back in Chem 4, there's this thing about electrostatic attractions. Do you remember that? So fluoride is it wants positive charge. What does fluoride want to pair with? Does it want to pair with another fluoride, a negative charge, or would it rather pair with something like a sodium with a positive charge? So should two fluorides come together, or would you prefer a sodium ion and fluoride come together? Yeah, probably something like that. And so when we look at cations, like let's pick a magnesium ion as an example, or let's go with something weirder. So if we pick a cation, which of these four will have the strongest attraction to the cation, or will they be equally attracted to the cation? Which of these four will have the strongest attraction to this cation, or will they be equally as attracted? I'm sorry? Yeah. Fluoride, we'd call it. Fluorine is the neutral. Why is that? Why would fluoride, you're correct, fluoride should have the strongest attraction to this cation because?
I think, excuse me, it's stronger toward the top right. I think it's progressively stronger.
That's electronegativity.
Oh, okay.
No, you're okay. But it's conceptually it's a little bit different because electronegativity we're looking at attraction for electrons. So fluorine has the strongest. But once fluorine gains an electron, then it's happy as is. It doesn't really want another electron because it doesn't have room for another electron. If fluorine gains another electron, it'd have to go in the next shell, which would be the third shell. Yeah.
Maybe because it's smaller, like if they're positive charge, it would be like more reactive to the positive charge than if it was bigger.
It is more reactive, but the question is, why is it more reactive towards the positive charge? That's what I was looking for.
Is it because there's like less electron shielding? What is it called?
Well, it's kind of like that, but shielding is a term reserved for blocking charge. When we talk about electron shielding, and we're talking about the inner electron shielding the outer electrons, that kind of stuff. This is not really shielding related. This is related to something else. This is like, let's say you have watered down lemonade versus concentrated lemonade. You know, is there a difference in the taste? Yeah, which one would be more like reactive to your taste buds, your taste sensors? The concentrated, even though they're both lemonade? Yeah? The concentrated stuff? Yeah, and so what would be more is what happens is we have dilute negative charge. This negative charge is spread out over this entire atom. This is more concentrated. And the most concentrated charge will be here. And so we call that the charge density. So fluoride has the highest charge density. Even though they're all negative charge, -1, highest charge density, whereas iodide would have the lowest charge density. And the more concentrated the charge density, the more reactive it is. So fluoride's going to be more reactive with cations. If it's more reactive with cations, that means it forms stronger precipitates or stronger solids. And so fluoride, there are too many exceptions with fluoride. And so I'm going to put a little asterisk here. And put an asterisk here. This is going to have stronger attractions with cations, so too many exceptions. So if there are too many exceptions, if you have a fluoride salt that you want to see, will it dissolve or is it soluble? Where would you check? What book would you check? Well, actually, I guess people don't use books anymore. But we used to have to use a book all the time because this stuff wasn't readily available. If you have a specific fluoride salt, what we would do is we use this book. There are a number of books. One of the we still may use this book. One of them is the CRC Handbook of Chemistry and Physics. Let's see. Are we on 95th edition? Maybe not. I think we're farther than that. (104th edition), 2023. 104th edition. This is the 64th edition. When was that? 6 pounds. This is from Wikipedia. So this has a lot of data that we would use. Okay, this is my crash version here. Maybe I have too many things. So we look in a book like the CRC Handbook. Let me see if I have an entry from the CRC Handbook, but I'll tell you what it looks like because the other book that we would consider looking at is the Merck Index. The Merck Index is more for biological and organic systems. And the CRC has, although it has organic and biological systems, it's mostly inorganic. Now they have the online. You have to pay a subscription fee for the Merck Index and CRC nowadays. So this has been going around for many years. They don't update this every year. So I'm not sure what edition we're on now, or if it's still being published. Here's an old one, the 5th edition. These are good. These are from the other option is just to use Wikipedia. A lot of the data, the Wikipedia is organized somewhat like the CRC handbook. And so if I go to calcium, let's go to calcium fluoride. And we can take a look at some of the solubility data here. So calcium fluoride is 0.015 grams per liter at 18 degrees C and 0.016 grams per liter at 20 degrees C. Probably at higher temperatures it's going to be increasingly soluble, but there's no data there. The solubility, acetone's an intermediate solvent. It's a nail polish remover. It's slightly soluble in acid, so they give you some additional solubility data there. Then you could look for more reference sources. The nice thing about the CRC is it's updated annually, and they have professionals who work at getting the most recent data to update it, and so that's why it's so expensive to book. There's the ionic lattice here, and the smaller the ions and the higher the charge, the stronger the lattice is. And so small ions like anions and cations make strong lattices because they have stronger electrostatic attractions. And strong lattices mean they are harder to dissolve in water and they are harder to melt. So when you see this 0.015 grams, for calcium fluoride, is that very soluble? What is the limit? What is the cutoff? When we say something's soluble versus insoluble, what is that limit? Does somebody remember? It's arbitrary. So when we use these are very qualitative. There are two ways we do solubility. We look at it qualitatively versus quantitatively. What is qualitative again?
Characteristics you pick up with your five senses, like descriptions and all that?
Well, the five senses is more like macroscopic versus particulate, usually.
Estimation.
What's that?
Estimation.
Estimation, yeah. So soluble means greater than 0.1 moles of solute per liter of solution. In other words, we're going to have greater than 0.1 molar. Slightly soluble means, this is S. SS means slightly soluble. And that's approximately 0.1 molar. And then we have insoluble. Insoluble means not zero. Insoluble means less than 0.1 molar. And so for something like calcium fluoride, that's less than 0.1 moles in a liter. And therefore, because it's 78 grams per mole, and so that's way less. And so that means calcium fluoride would be insoluble in water. Do you remember the others? Since we're doing this, we might as well just finish this. after sulfates comes,
Oxide, solid,
hmm?
sulfide, phosphate.
Yeah, hydroxides. Hydroxides, on the other hand, are insoluble. Most of them are. And so insoluble except which ones? Yeah, ammonium and group 1. Ammonium. Actually, I'm just going to spell it out. Ammonium. Calcium. Calcium, strontium, barium. I'm just going to go in the order there in the periodic table. Strontium and barium. All right, now sulfides. Sulfides are insoluble except group 1. That's why we look at group 1 first, because group 1 and ammonium are all soluble. Group 1, ammonium, and group 2. And so we have this. Do you see this? What happened to magnesium? You know, I'm going in the order calcium, strontium, barium, but beryllium's missing. Beryllium's missing for good reason. Beryllium's very toxic. But magnesium, what happened to magnesium? Magnesium's not so toxic. People take magnesium supplements. What happened to magnesium? Why is magnesium missing? Did I unpause my recording? Yeah, I did. Yes, right. Magnesium's the smallest of those. There are too many, what? Exceptions, you know. Because the magnesium, calcium's bigger, strontium's bigger, barium bigger. And so these are the things, you know, there are two ways to learn it. One way is the first way, you just memorize them. Okay, but after you memorize them, then you start looking for patterns. Because the reason you want to look for patterns is because not all questions come from recall of memory. There are a lot of questions that are going to ask you to come up with, you know, an answer. And if you know some patterns, you'll be able to answer a lot more questions than just straight memorization. Okay, the last, number 7. Phosphates. Chromates. Although I don't normally go in this order. I usually go phosphates and then carbonates and chromates. Insoluble except for group 1 and ammonium. What do these three have in common, kind of? What's special about phosphate? Why would these be so insoluble? High negative charge. What's the negative charge on phosphate? 3 minus, yeah. So these high negative charge species are negative 2, negative 2, negative 3 are going to be more reactive. Negative 2, this is negative 1 hydroxides. However, it's small. Hydrogen's tiny, oxygen's pretty small. Sulfates, those are negative 2, but they're kind of big. You know, because you have a sulfur with 4 oxygens around it, so it's a little bit big. But what about this? Silver. Silver is not that high of a charge. Look at these are all high charge cations. High charge, except this one. That's not that high charge. Now silver is what we call heavy metal, and so the bonding is less what we call ionic and more covalent in some of those heavy metals. So the bonding, when we're looking at these ionic lattices, we're looking at electrostatic attractions. Electrostatic attraction is a purely ionic bonding. We could also have some covalent bonding, and so that's why this is a low charge. Silver ions are very small though. So silver ions are small, low charge, and plus they're heavy metals, so there could be more covalent interactions, and so there are more exceptions. And these types of things we look for in the pattern. So first, in science, we take our observations, and then we look for patterns, and then we start to think, you know, a hypothesis. Why are these soluble? Why are these insoluble? You know, and then we should come up with some theory. The theory here is bonding theory, but we're not going to get into that quite yet, you know. We're just going to keep moving. And so if we have a sulfate, so the question is, this sulfate, our unknown sulfate dissolves. That means it cannot have, it might have silver, but likely it doesn't have silver. For sure it doesn't have lead, it doesn't have mercury 1, mercury 2, calcium, strontium, barium. We can't have these present and have it dissolve, because if these are present, it won't dissolve. Does that make sense for that? And so we get some clues here. It dissolves in water. And you don't even need hot water, but we're going to go ahead and dissolve this. Right now the sulfate is locked in a crystal lattice, so I'm going to just call it solid. Solid state means there's no translational motion. And then we're going to dissolve this just in water. And it's going to free up. This. We're also going to put some acid in here. In fact, we're going to do it both at the same time. Water and acid. Now, what acid are we going to put in there and how much? And why are we putting the acid in there? The acid, the purpose of the acid is not to dissolve the sample. The purpose of the water is to dissolve it, to get sulfate aqueous. Plus, we're going to have other cations and anions aqueous. Maybe other anions, we don't know. But for sure other cations. The purpose of the acid is to prevent interfering precipitates. Acid, you know, we got H plus in here. Or what acid? Let me see what acid we're going to add to this. Let's save that. And so I would go down here to the procedure and let's take a look.
What pages experiment is in the
The pages aren't numbered. Are the pages numbered in this book? Oh, it's page 6. I'm on page 6 of experiment 1. Do you see it? So we're going to add hydrochloric acid. And we're going to use 6M, 6 molar hydrochloric. We need to know how much hydrochloric acid is in there. So hydrochloric acid is what we call a strong electrolytes. Strong electrolytes ionize or dissociate in water. So we're going to have hydrogen ions or hydronium and chloride ions in water. Hydrochloric acid at 6M. 6M is what we call dilute, but if you spill some on you, you know, it could still sting a little bit. If you spill any hydrochloric acid on you, and I've spilled lots of hydrochloric acid on my hands, what you want to do is just wash it off with plenty of water, and soap and water usually. Soap and water is good for washing off hydrochloric acid spills. Let's say it splashes in your eyes. So you get some hydrochloric acid in your eyes. You know what you should do? 911, this can take too much time. It'll cause damage before then. Yeah, we need to irrigate your eyes or wash your eyes. We have this. This is our eye wash fountain here. And so you'll go here. I would show you this. However, it is, there's no drain here. It's just going to drain on the floor. I don't want to drain it on the floor. The other thing is, at your lab station, do you have a hose? Yeah, you have an eye wash at each of the sinks in your lab station. I don't have one though, so I guess I'm supposed to go there. But if you splash something in your eyes, are you going to be able to see when it's burning your eyes? You're probably not going to be able to see because your eyes are probably going to be clenched tightly closed. So if you see somebody with their eyes tightly clenched closed, you might have to help them over, you know, over to the eye wash fountain and then start irrigating their eyes. Or if you're near the sink, do you see the eye wash? Can somebody pull one out? Just pull it out of the. Have you guys used these before? Yeah, and then just pull the handle. There's covers on there to help protect it, but you know sometimes the covers are off. So just irrigate some water first before irrigating your eyes. I mean, just rinse out the heads of that. How long do you need to wash your eyes out? Let's say I got some hydrochloric acid splashing in my eyes. How long do I need to wash my eyes out for? Until the ambulance arrives. Could be a long time here. Although, the police will come, and then they'll probably take you. Actually, they have. It's happened before where we've had a student, and the police came, the campus police came, and then they drove them to Gardena Hospital there on Redondo Beach Boulevard. Yeah. It's happened before. We have a health center too. The health center is not that far. They moved. They used to be next to the pool, and now they're over here in a nice building. You could go there as well. Somebody could help you there, depending on how much it's burning. But you're supposed to irrigate your eyes for a minimum of
15 minutes.
15 minutes. 15 minutes. 15 minutes is awfully long, but you have to do that because your eyes are like sponges. And how long, let's say some hydrochloric acid got onto your wet sponge. How long do you have to rinse the surface of your wet sponge for to remove the hydrochloric acid that got absorbed into the sponge? Well, at least 15 minutes. You might just wash it on the surface, but it doesn't take the stuff that got inside out. And so that's why 15 minutes. 15 minutes sounds ridiculously long, and probably after a few minutes, your eyes start feeling better, but you should still rinse for the full duration, which is especially long. Most of the splashes happen when it splashes up, and gets under people's goggles and gets in their eyes. And so, let's say you spill the whole bottle of hydrochloric acid all over you. Then what should you do? Like your clothing is saturated with hydrochloric acid? Yeah, you want to go to the shower here. And this is the shower here. And you just pull this handle down, and then a huge stream of water will come down. There's a safety video, which I decided I'm not going to show so long. But they show you, you're supposed to remove your clothing because your clothing's contaminated. But that's happened where somebody spilled concentrated sulfuric acid on their pants. And the safety shower, but the concentrated sulfuric acid was soaked into their jeans. And the safety shower, it's like washing out a wet sponge. It's going to take too long, you know. And so that person went into the bathroom, but the bathroom sink is not like a shower. And during that duration, ended up getting burns. With concentrated sulfuric causes third-degree burns, potentially, if you don't get it off. Second-degree burns are pretty easy with concentrated sulfuric acid. That happened in our old building. So our new building now has a private shower with a shower curtain. So if that happens again, you know, if it happens to you, you go over here, you do this, and then you can go to the private shower. Private showers behind the lecture rooms, and you can remove your contaminated clothing and make sure you rinse thoroughly off. Okay, so spills, and we do that. Hydrochloric, though, is not so bad. I've spilled lots of hydrochloric acid. At 12 molar, it's kind of bad. At 6 molar, it's not terrible. All right, so the first step is we need to free up the sulfate. The sulfate was locked in the lattice, the solid here. And so now we've freed it. And so now the sulfate's free, it's got translational mobility, it's in the aqueous phase. And now what we're going to do is we're going to capture the sulfate. How are we going to capture the sulfate? How we're going to capture it is we're going to react it with an ion that sulfate likes. The sulfate, do you think it likes sodium ions? Yeah, but you know, sodium and sulfate will come together if it's like fish in a pond. You know, sodium ions are like a fish and sulfate ions are like a fish. Are they going to come together in a big pond? No, what you have to do is you have to evaporate the water. If you keep evaporating the water, the volume of the pond goes down, and pretty soon the fish are going to come together because there's no more water left, right? And then they're going to be together. That's like sodium sulfate. Sodium sulfate is what we call soluble. We can precipitate it out by evaporating all the water. If you evaporate the water, you're going to force the sodiums and the sulfates together. We don't want to force the sodiums and sulfate together. We want a cation that's very strongly attracted to sulfate. We want a cation that's so strongly attracted to the sulfate that it clumps onto the sulfates and then forms a precipitate. And the precipitate comes out of solution. So give me a cation that likes sulfate. Actually, give me a list of cations that really like sulfate. Calcium's one. Give me the whole list. Yeah, strontium, barium, calcium, strontium, barium, mercury, lead. So I have this pattern. I always use the same pattern. Silver, lead, mercury, calcium, strontium, barium. This makes it easier for me to memorize. So we could use any of those. So for example, if we put in lead here, lead loves silver. Lead and silver come together, they form lead-2 sulfate, which is a nice precipitate. Lead-2 sulfate, I think they use as a white pigment in paint. It's a really nice white solid. But people don't use lead-2 sulfate for paint pigment anymore because of its toxicity. So we're not going to use lead. We're not going to use silver. Silver stains everything black, and it's a heavy metal too. So if you get it in your blood, you don't want that. In fact, I had I know somebody was taking silver, some kind of silver supplement, and their skin turned green. Have you ever seen that? Yeah, there was some kind of it was being sold as some kind of immune supplement or support, and so he started taking this. And then eventually his complexion turned green, and then it took about 4 years for him to lose the green. It was very bizarre, though. You might, think alien or something like that. But we're not going to use silver. Calcium would be good. Strontium, we don't want to use. There are some radioactive isotopes of strontium that get mixed in with the non-radioactive ones. Strontium, there's strontium around from like things like Fukushima, and I don't know if Chernobyl released strontium, radioactive strontium, into the environment, but there's, some radioactive strontium mixed in with the regular strontium. But you know what we're going to use? We're not going to use calcium. We're going to use barium. Now, one of the reasons why beryllium is so toxic, did you know beryllium's super toxic? But it's kind of takes time. Because what happens is, your body needs calcium and magnesium. But if beryllium gets in there, it's much more aggressive. Why is it much more aggressive than calcium and magnesium? Because it's smaller. It's very small. And so beryllium we don't use. They used to use it a lot in aerospace because beryllium metal is like magnesium, very lightweight and structurally strong. So they used to use it in aerospace as a structural material. And so all the machinists that were machining beryllium metal ended up, like, when they got closer to retirement or 20 years later or 10 years later, ended up getting all kinds of physical ailments. I think cancer is the big one. And that was due to beryllium poisoning. It wasn't acute, like it didn't happen immediately. It took time for it to occur. Well, barium, one thing about barium, look at barium's position in the periodic table. As we get lower and lower, barium is kind of like a heavy metal. And so barium is not exactly non-toxic. And so we're going to add barium chloride aqueous to this. And so barium chloride, watch out. It could cause potential problems. You don't want to touch this stuff. Barium, because barium ions can also cause trouble. In a different sense. The bonding's a little different than beryllium. But we need magnesium and calcium. We don't want any strontium. And we don't want any barium and beryllium. However, did you know I had to drink barium sulfate? I went for a CAT scan, and they gave me a glass of barium sulfate. And the barium sulfate, is barium sulfate very soluble? No. And so when I drank it, it was like chalk, board chalk, crushed up, powdered in water. So it was like a dry, chalky tasting mixture, But the barium sulfate is quite stable, and so the barium sulfate wasn't toxic. Barium sulfate's generally regarded as safe. Generally regarded as safe as GRAS, G-R-A-S. But barium chloride is not generally regarded as safe because barium ions, they're free here. They're not bonded to the chloride. This is, strong electrolyte. Soluble salts are strong electrolytes, so the barium ions are free to react with other species, like sulfate. And so the barium and the sulfate come together and we precipitate out barium sulfate. But when we precipitate it out, it forms a very cloudy precipitate. It's a white PPT. And this precipitate is called a colloidal precipitate. It's like milk. If you look at milk is what we call a colloidal mixture. There are particles in milk that are quite big, but these particles are small enough that they stay suspended. And the same thing with this. Colloidal precipitates will stay suspended. This is like muddy water with a very, very fine silt. And so it stays muddy. It takes a long time for the mud to settle to the bottom. The situation with this is we could wait forever and it doesn't settle to the bottom. The crystals are so tiny they stay permanently suspended in the water. And so what we have to do is, when we end up with a colloidal precipitate, the particles are so small they stay permanently suspended in the water. And so what we want to do is we want to do a process called coagulation. And so we want to take the tiny crystals and coagulate those into larger crystals. Once it reaches a certain size, the coagulated crystals will fall to the bottom. Due to gravity. When we do that, if these nicely coagulate, then we're going to get a clear solution above, like this, and the precipitate below. And so it's like the fog lifts, you know. When you're in a fog and the fog lifts, then all of a sudden you can see. All of a sudden you'll be able to see the water. Actually, it's a solution. And so we need to coagulate this. And so what you're going to do is this. We don't want to add too much barium chloride, and we don't want to add too little. How do we know we've added just the right amount of barium chloride? How we know we added just the right amount of barium chloride is it stops precipitating, it stops getting cloudy, but pretty soon it's so thick, the clouds are so thick, can you even tell if you're getting more cloudy or less cloudy, or is it easy to see? No, it's so hard to see. So this becomes it's like whiteout. And if you're in a complete whiteout, you can't see anything. And so you're adding drop by drop barium chloride. Drop by drop. And you got to make sure you don't add too little. And you got to make sure you don't add too much. And the problem is it gets so cloudy you can't see anything. And so when that happens, you got to coagulate. And how do you coagulate? Have you ever seen this symbol? Heat, yeah. For heat. So we heat it up. When you heat it up, what happens? It increases. Heat is related to what? Heat is a measure, or temperature is a measure of energy. What kind of energy? Thermal energy is heat, but we have two types of energy. What are those? Kinetic and potential energy. So we increase the kinetic energy. Kinetic energy is the energy of motion, right? Yeah, motion. So we heat it up and then we get collisions, and these collisions will conglomerate these particles into bigger ones, and then it falls. And so this is what we do. Now, once it's coagulated, we remove from heat and let it settle. Let the precipitate settle, and then we test it again with another drop of barium chloride. And then watch. When this drop of barium chloride hits the surface of this, do we get more precipitate? If we get more precipitate, then keep adding. And so you're going to have two things happen. No precipitate, then you're done. It's done. More precipitate, keep adding. You got to keep adding until you're done. Uh-huh.
Can you repeat that again? What does the heat do? Is it like moving the precipitate that's suspended in the water and making them be closer together?
The heat just increases the kinetic energy. And so what happens is, on colloidal particles, there are surface ions that attach to the colloidal particles. This would be like a pre-lab question at UCLA. You know, talk about colloids and their interactions, this kind of stuff. So this is discussed in the procedure. So normally what we do is, you know, you'd read through the procedure, but what happens is it accumulates, let's say, negative charge on the outside of these tiny crystals. If it accumulates negative charge on the outside, are these tiny crystals going to be attracted to one another, or are they going to repel one another? They're going to repel one another. Like charges repel, opposite charges attract. However, what we're going to do is we're going to use kinetic energy and force these to collide with one another. And so the heat, what it does is these are going to naturally repel, so we're going to use the kinetic energy to overcome the repulsions so that they collide. When they collide, then the positives and the negatives can see one another, and then they can stick to each other. They get stuck. And so what happens are the crystals get stuck to one another, and more crystals get stuck to one another, and pretty soon we build a big clump of crystals. That big clump of crystals will now fall down to the bottom of the beaker. We're going to heat using not Bunsen burners in this class. We're going to heat using these hot plates that are located in the center. Now the hot plates are tough to use because they take so long to warm up. So probably the first thing you should do is just crank up the heat. But the second problem is if you crank it up to 10, it's going to get too hot. And then you got to crank down the volume, and it takes time to cool down. And so I would just go ahead and crank it up to maybe 8, 9, 10, and then as it gets hot, then cool it down a little bit. Does that make sense? So I'd probably do that first to get the hot plate hot. And we're just going to place our beaker on the hot plate and just heat it up. And so today we're not doing too much stuff. And so this is what I do in lab. We have to measure the solid. Now, weighing out the solid is going to be tough. So what we're going to do today is we got to just make sure we precipitate out everything here. And then we're going to stop here for today. Now, weighing out the solid is difficult because, you know, these crystals have ions, and the ions can attract water molecules. And so what happens is, even though the crystals might look dry, there could be a water molecule or 2 or 3 stuck on the outside of these crystals. And some water molecules can actually wiggle inside the crystal lattice. You know, it's like a maze. And the water molecules can find its way into the maze and get stuck. We call those types of crystals hydrates, where water gets stuck in the lattice of the ions. And so we don't know if our unknown is a hydrate or has surface water or whatever. And so what we do is this. We have to dry the unknown. And you don't have to. The stockroom did this for you. And the stockroom did this by heating it. And they're going to heat it in something called a weighing bottle. A weighing bottle has a cone type lid here, with a cap. And this is all made of glass. So you'll have a matching lid, and the lid is also going to be a cone type. Like this. This is called a ground glass joint. And so it's polished glass. And it provides a nice tight seal here. And so you're going to get your weighing bottle, it's going to be hot, with the lid on the bottom like this. Now, if you're, this is the unknown. This, I should do it a different color, because barium sulfate is your precipitate. We'll do your unknown in blue. It's going to be hot because it's going to come straight out of the oven. The ovens are located in this little room here between us and the balances. And so you'll grab a tray, and then they're going to give you your unknowns. They're going to give you 3 unknowns. You're going to work in groups of 3. We don't have enough equipment. It used to be, I used to have people do this individually, run 3. But now we're just going to have a group of 3. And that's because we're going to have these. These are Celis crucibles. Actually, we don't need the crucibles today. We need this. So you're going to have something like this. This is the ground glass joint. You twist this off if you want to get it off. Sometimes it gets stuck. It's hard to get off. But you're going to get it like this. It's going to be hot. Why do we heat it up? We heat it up to drive off the water. What happens if it cools down? It's going to just reabsorb the water. We don't want it to reabsorb the water. And so what you're going to do is this. The problem is this. If it's hot and you put the lid on here and the air cools down, the air, as it cools down, contracts, it creates a vacuum. And so we get a vacuum here, it's hard to break the lid. Just twist it, and you'll be able to break it. But this is what I recommend. I recommend is when you get this hot, you put the lid on. That'll prevent it from reabsorbing water. Does that make sense? Okay, you can handle this with your fingers once it cools down enough. It's out of the oven, it's only 110 degrees, I think, out of the oven. So it's going to be hot. You wouldn't want to handle it with your fingers, but once it cools down enough, then it should be all right. Also, you shouldn't drink or eat in lab because, you know, I might have spilled some unknown in here, so I'm probably going to dump this and wash this. I don't know what's in the unknown. There's no lead, fortunately, in the unknown. So no eating, no drinking. Also, did you guys able to get your goggles from Chem 4, wherever? And then you have to wear proper footwear too. No sandals in lab as well. Because hydrochloric acid we don't want to spill. Although that's, I don't know. It's easier to wash off bare feet than get it soaked in your sock or something like that. But then there's broken glass. Okay, so we do this. Now we got to weigh this. The old procedure, we actually weigh the weighing bottles. This procedure, we don't actually weigh the weighing bottles. And the amount is going to be given on here. How much do we weigh? It's in the procedure. And so what I do is to save time, I do this. I put in approximately the mass required, and then approximately how much water is required, and then how much HCl. And so what I do in my notebook, I do this before coming into lab. I'll write down how much solid do I need to weigh out? How much water do I need to add? How much HCl do I need to put in there? How long do I have to heat it for? I'll put all those details in there. Then during the lab, things change. Maybe I weighed a little bit more. It's no big deal. If you overshoot it, you're fine. You could overshoot it by about 20%, you know. But make sure you get all, we need an accurate mass, so make sure you get all the digits here. And so usually I write that in a different color pen. And so the procedure I'll write like and you're supposed to write this in ink as well. And so the procedure I'll write like, okay, weigh out this many grams. But let's say I didn't weigh out that many grams. Then what I'd write below this is actually how many grams did I weigh. You know? And so it might say weigh out, you know, actually this is going to be 0.5 to 0.6 grams. And I weighed 0.4378 grams. I'll write 0.4378 grams here. So this is the difference between procedure and observation. Procedure is what you should do. Observation is what you actually did. And so procedure is what you should do. Observation is what you actually did. So you should run on the treadmill for 30 minutes. Well, I only ran for 5 minutes. You know, that's the difference between procedure and observation. So we want to write what we actually did here. Actually, 0 minutes is usually what I do treadmill. But the same thing with the water, same thing with the acid. And so what we're going to do is we're going to weigh these out. Now, our balances can tear a beaker. And so what you could do is you could put a beaker on there and zero it. And then what you do with the weighing bottle is you just, I usually do this. When I'm about to weigh, I'll undo this. And I'll try to do this quickly so it doesn't reabsorb a whole bunch of water. And so then I'll tap it in like this. Sometimes I accidentally overshoot. If you accidentally overshoot, just keep it. You know, if you overshoot way too much, then we'll have to dump some out. And so be careful. Okay, but to prevent this vacuum from occurring, we're going to use one other thing, piece of equipment. Have you ever seen one of these? This is called a desiccator. And check this out. This has a flat lid on the top. Watch, I'm going to hold this 90 degrees here. Do you see the flat lid? Doesn't come off. It doesn't come off because it has a ground glass joint with grease on it. So to remove the lid, you have to push it off here. And then you'll see a ground glass flat joint there with grease on it. We usually grease the lids, but you aren't, grease the joints, but we aren't going to grease this one here. This is called the desiccator. In the desiccator, we have desiccant. The desiccant absorbs water. Our desiccant is good. If you see blue, it's good. If you see pink or red, it's bad. And so this has the capability of absorbing more water. And so out here, it's like 20%, 30% humidity. Inside here, it should be 0% humidity. And so what we're going to do is this. Rather than put the lid on while it's hot to prevent water from getting reabsorbed here, it could be difficult to remove this. What we're going to do is we're going to put the lid down like this, put this on top like that, and then put it in the desiccator. Unfortunately, we don't have enough desiccators here. Okay, now we're going to let the sample cool in the desiccator. I don't have to break the lid because this one's a lot easier to remove even if there's a vacuum there. So it says wait. Leave it open. Well, I'm not going to leave it open for very long. I'm just going to put the sample in there and then let it cool down. Okay, once it's cooled down so that I can touch it, it doesn't take very long to cool down. I'll remove the sample out here and then seal it with the lid and then go weigh these. Bring my since each one of you is just doing one sample, bring a beaker out there and weigh it. However much it says to weigh in the procedure. But like I said before, rather than digging in the procedure to find it, it's easier to do this before. Now, everybody's going to use the same sample, so one person has to weigh theirs and then give it to the next person. The next person weighs there and then give it to the third person. Third person will weigh it. Is that clear? All right, once you get the sample, then we don't care. We have the dry weight. We call dry solids anhydrous. So we have the anhydrous versus hydrated. We don't want it hydrated. And so once we weigh it dry, then I don't care if it reabsorbs water. I know how many grams I have of dry solid in here. That's why we don't care. We're going to dump in a whole bunch of water to dissolve it next. And then follow this procedure along. Okay, any questions on this? All right. So today's It's not too complicated, I think. So go ahead and crank up the hot plates, and then you go to the stock room, one person per group of 3. And unfortunately, we have to do this for groups because we don't have enough equipment. So everybody's going to have to work in a group. We might have a group of 2. I'd prefer not to see a group of 4 though. And so it's either going to be a group of 2 or a group of 3. All right. If you have like drinks or stuff, you probably should put it away. We have some lockers there. You can put your stuff away. You can go outside and drink, it's no problem. If you forgot, 1B. If you forgot your goggles, we have some spares you can use here. Just clean them.
Professor, on Wednesday, I'm not going to be here because we have to second part of the lab, so
Can you come in the afternoon, one day?
around what time? Depends